Two.
Hello, I'm Nick Moore, and I'm recording Proof 4.3, set to the righteous tunes of a cover of Harvest Moon by the band Teen Days. This will be a very chill proof set. Alright, so today we're proving that using the Bolzano wire stress theorem, a continuous real-valued function, f, is defined on a compact subset C in our event. Such a function has a supremum m, in that there's a point that A, which is an element of C, which is maximum, where f of A equals m. So our proof has two parts. The first part, the most excellent first part, is to prove that f is bounded via contradiction. We do this by taking the thought experiment of Giulio camping in the Rocky Mountains, perhaps with his friends, perhaps by himself. We don't really know who Giulio is, but we do know one thing. He has a mission. He wants to move to the highest peak in the Rocky Mountains. So let's say on night I, he is staying in a camp. He is staying in a camp, an altitude defined by f of xi, which of course is greater than the value of I. So this gives us a sequence x1, x2, x3, and so on and so forth, x4, x5, and we know that by Bolzano Weierstrass, we can extract a convergent subsequence. Because from this compact set, which again is the set of x values, so the ordered pair of coordinates in the Rocky Mountains. So we do this as follows. We can just take the x1 of y1, y2, y3. So obviously, trivially, if we have yi equal xi plus k for all k that are greater than or equal to 0, and we define as yi as converging to b, then we also have fy of I equals f of xi plus k, which we defined earlier to be greater than 1. So if we suppose that f is not bounded, then what ends up happening is we continue to increase to infinity, and we will never converge to any given value because f is not bounded. So we call this y1 being a bad sequence, and according to proof 4.2, the existence of a bad sequence means that the function f must be discontinuous at b. Such chill music. Alright, so this of course is a contradiction of the given condition that f is continuous. So f has to be bounded. Cool. All right. So part 2. Now we know that. Well, what we want to say. We know that f is bounded, so we need to say that a non-empty subset of the real numbers has the least upper bound m, which is a supremum. So we say that, going back to our earlier idea, that Giulio is camping each night closer to M. We can define this with an example function like this. For instance, so he's moving as I increases, the difference between M and Giulio's altitude decreases also. So once again, we can take a convergent subsequence. Let's define y of a converging to a. Sorry, y of y sub I converging to a on f of a equals m. And just from the way that we constructed f, we know that f of y1 has to converge to m, because we're using a good sequence on a compact set. So, in other words, y1 is good because f is continuous. Therefore, if we take the limit as I approaches infinity of f of y sub I, we know that it's equal to m, and that that is in turn equal to f of a. Therefore, there exists a supremum called M, and it is also a maximum. That's a wrap.